Prove that the relation R on the set of integers Z defined by the ordered pair A comma B belonging to the relation R if and only if 5 divides A minus B is an equivalence relation on Z. Okay, now let's try to understand the problem first. So here it's mentioned that the relation R on Z. So simply means that R is going to be a subset of the Cartesian product of the set of integers Z with itself. Okay, and here we have to define R. So R is defined as the set of the ordered pairs A comma B such that A and B are integers. A and B both belongs to the set of integers Z, and here we have 5 divides A minus B. Okay, so we're going to use this. So we have to show that this is an equivalence relation on Z. What does it mean when we say a given relation R is equivalence relation? It simply means that the relation R is going to be reflexive, it is going to be symmetric, and it is going to be transitive as well. Now when we can say that a given relation follows all of these three relations, then we can immediately say that our relation is going to be an equivalence relation. So let's quickly recap the three types of relations. So let us suppose that R is a relation on the set A. Then R is going to be reflexive if and only if the ordered pair A comma A belongs to the relation R. R is going to be symmetric if we have the ordered pair A comma B belonging to the relation R. It implies that B comma A also belongs to the same relation R for all values of A and B belonging to the set A. And then finally R is going to be transitive if the ordered pairs A comma B belongs to R and B comma C both belongs to the relation R. Implies that A comma C also belongs to R for all values of A, B and C picked up from the set A. Okay, we'll start with the first one by checking whether if our relation R is reflexive or not. So here what we'll do, we will assume an arbitrary element. So let A be an arbitrary element in the set A such that if we consider the ordered pair A comma A belonging to the relation R, then this must imply that 5 divides A minus A. Now we know that 5 dividing A minus A simply means that 5 divides 0. Is it a true statement? Yes, that's definitely a true statement. 5 indeed divides 0. So here we can say that our relation R is reflexive. This is a reflexive relation. Okay, now we'll check whether if it is symmetric or not. So that means here we need to start with an ordered pair. So let's say we have the two elements A and B. So let A and B belong to the set A such that if we consider the ordered pair A comma B belonging to the relation R, then this must imply that 5 divides A minus B. That is the definition of the relation that's given to us. Now can we now say if 5 divides A minus B, in other words we can also say that A minus B, this is going to be a multiple of 5. So here we can simply represent as 5 times lambda, where lambda, where we are saying that where there exists some lambda, belonging to the set of integers such that A minus B equals to 5 times lambda. Fine. Now what we can do here is we can also rewrite it as B minus A equals to negative 5 lambda. All we have done is multiplied both sides with negative 1. Now we have B minus A equals to negative lambda multiplied to 5. Now lambda is an integer, so negative lambda is also going to be some integer. We don't have to worry about its value. But here this tells us that B minus A equals to negative lambda times 5. This tells us that B minus A is a multiple of 5. Or in other words, what we are saying here is 5 divides B minus A as well. So since 5 divides B minus A, this is simply the definition that the ordered pair B comma A belongs to the relation R as well. So what does it tell us? So we started out by considering the ordered pair A comma B belonging to the relation R, and we were able to show that the same ordered pair B comma A also belongs to the relation R. So here we can say that our given relation R is symmetric as well. So this is a symmetric relation. And finally, we're going to check whether if it is transitive or not. Okay. Now to check for transitivity, we need 3 elements. So let us consider those 3 elements be A, B, and C. These are the 3 elements that belongs to the set A, such that if we consider the ordered pair A comma B belonging to the relation R And we also consider another ordered pair. We have to be very specific how we choose the next ordered pair, the second ordered pair B comma C, which also belongs to R, such that the second element of the first ordered pair A comma B must match with the first element of the second ordered pair. So this must imply we must show that A comma C, the ordered pair A comma C, also belongs to R. This is our goal. Okay, so since A comma B belongs to R, this simply implies that 5 is going to divide A minus B. And B minus C belonging to R simply means that 5 divides B minus C. Okay, fine. So now we have A minus B. This is going to be equals to 5 times lambda. We are assuming that A minus B, 5 dividing A minus B is also the same as saying A minus B is a multiple of 5. Similarly, 5 dividing B minus C can be also expressed as B minus C equals to beta times 5, where we're saying that B minus C is a multiple of 5. So we have to mention where there exists some lambda and beta which belongs to the set of integers. Okay, now what we'll do, we will solve this to equation and we're going to eliminate B. So here let's isolate B from the first equation. We get B equals to A minus 5 times lambda, and we're going to substitute this B value into the second equation. B minus C equals to 5 times beta, so that gives us A minus 5 times lambda minus C equals to 5 times beta, or we can say A minus C equals to 5 multiplied to lambda plus beta. Now lambda and beta are already integers, so the sum is also going to give us some integers. So here we have shown that A minus C equals to 5 times some integers. So in other words, we are saying that 5 divides A minus C. This simply implies 5 divides A minus C. Now 5 dividing A minus C is the definition of the relation. That means A minus A comma C, this ordered pair, belongs to the relation R. So we started out by considering two ordered pairs, A comma B and B comma C, which both belongs to the relation R, and we are able to show that the ordered pair A comma C also belongs to that same relation R. So this tells us that our given relation R is transitive in nature. Now this is a transitive relation. So since we have been successfully able to show that our relation R is reflexive, symmetric as well as transitive, thus we can say thus R is an equivalence relation. This is an equivalence relation on the set of integers Z.